Yeah, so this is the working group that we have put together in the last few weeks. This is the first time we're trying it out. Matthew is going to be doing like a high-level intro to zkStudyClub, which I think we've all been very excited about. We have had a little bit of trouble getting the sound and video set up. Well, we'll definitely try to find another setup for next time, but we hope that if people are watching this after, that you can at least understand it. And yeah, you might want to join us next time. So I think that's maybe the way I would start. And Matthew, if you want to maybe just do a quick introduction about what you're covering today, that might be helpful too.
All right, yeah. So for the kickoff talk, we're going to look at the last presentation that Eli Benzazon did at Web3 Summit. So I took some detailed notes. Alex, who's not on the call, but he also had some very detailed notes. So I think I'm using a combination of what we wrote as we were watching that talk. It's meant to be a bit of a high-level overview. It's also taking, it's basically what he talked about for those of you who've already watched it. So it's an overview of where he and his team are at with Starks, but it's also dipping into Snarks and Bulletproofs. Mostly because those are the most famous or the most known kind of use cases, or there's use cases of it out there in the world, so that's why those three are being talked about the most. Certainly there are others, and it's such a hot space right now for research. It seems that the amount of papers coming out over the last years is increasing, which is fantastic and makes for lots of good evening and weekend reading, I guess, for all of us. So if there's no other remarks, then
do you want to just are your notes something you can share?
Yeah, absolutely. So this is just a markdown file, and there's another document here that Alex had shared of his notes. So at the ending we could share both of these. I need to publish mine somewhere. Probably I'll put them also on Google Docs because that seems to be where we're sharing everything.
I'm looking for Alex's notes here, but did he post them somewhere, or he just shared them directly with you?
He did send them as a DM at 4 a.m. my time, so I don't know where he is, but I was just looking over them as we were waiting to start.
Okay. I'm just wondering if there's something we can follow along, but we can also do this after.
I mean, I could do it really quickly. We'll see. Yeah, for those of you that want to read, let's do this. Let's do. So Telegram came up. So here are the notes of Alex. I guess it's okay to share them. Hopefully he's not. Hopefully that's okay. Alex. Sharing the notes you gave me. If that is okay. And if I make a new one. This is my machine struggling.
That looks good. Thanks for that.
Great. It's not sending this one though. Warum? There's something there. There we go. Alright, that's just my machine struggling. Cool, and here are my notes.
Amazing, thanks.
Okay.
Yeah, looks good.
Okay, so mine are in Markdown, which is why I'm going to, I guess, present off of this screen. And I'm going to switch over to Alex's when we get to the demo because he did a really great job breaking it all down. All right, so let's get into it. So the main link, and also this is something that got recommended in the Telegram channel, was zkp.science. That seems to be a really good collection of papers. So I think if we wanted to rally around a resource, maybe we could start opening up pull requests there for other papers that we find interesting. I know that possibly in our group we will do something else, but that seems to be a good starting collection. So the way that that Eli was describing it as how to talk to the general public about what is a zero knowledge proof. He had this good metaphor of it being like a grocery receipt. So you have a list of items with a price, and it's summing up to a total. And this is a nice, mathematical statement that you can make, because it's very obvious that you could give anybody this piece of paper, and they would be able to say, okay, as long as I have all those items, in my grocery bag, then I know that this transaction we just had was correct. You're not lying. There's nothing missing, and this is in fact the total which I'm about to pay you for. So this is quite nice as a metaphor then into zero knowledge proofs, because if you're wanting to be the prover, you could be choosing that some of those items, some of those prices on this receipt are private, and you're going to blank them out, and you could still trust the total amount due to the mathematics behind how the proof itself is working. So this is quite nice if you're trying to, I don't know, talk to your friends or significant other, or maybe parents about what it is. I thought that this was a nice metaphor. So I guess starting off with the general overview, the first instance or the first paper of zero knowledge was in 1985, and was a collaboration research of MIT and University of Toronto. So Shafi Goldwasser and Silvio Micali and Charlie Rakoff. And since 1985, there has been many more advances, but this being the first, Goldwasser and Micali got Turing Awards for their works on these kind of proofs. So it is quite nice, I guess, that we're building on something that is so old, even though there are some constructions that are quite new. There's been enough time, I think, for research to be done on this. Then, yeah, why would you want to use this, or what are some examples that one could prove? I guess looking at the blockchain space is a really good candidate for this. That if you were wanting to prove to the government or whoever it is that is your tax authority, and you wanted to make a statement like, I paid all my taxes on cryptocurrencies last year. This is something that is possible because when all of the transactions have been done on a public ledger, you could construct a proof such that the public inputs are available. And I think that this is really this is really nice. I don't know if all banks in the near term are going to be using blockchains, but certainly this is something that becomes possible in the future for private individuals to make statements like this. Yeah, something else that is also kind of important in the blockchain space is crypto exchanges themselves being able to make a statement that they are, so-called in the black, that they are, they're holding enough reserves for all the funds that they are supposed to be controlling. And you could swap crypto exchange with banks, and this is in fact what they're supposed to do. They need to keep a certain amount of value in reserve. They can't leverage 99% of all the value that they're supposed to be keeping track of. Yeah, so the quick facts, I guess, about zkStarks is that in the past 5 years, I guess this is Starks and Snarks in a way, but in the last 5 years, there's been a number of developed basically software libraries. I'm going to say of varying quality. I've seen more of the research academic libraries being said as, warning, this is alpha software, it doesn't have a security review. It's good. It's definitely good enough to play with, and and probably not something you want to deploy in production because of security concerns, but additionally, they haven't been optimized, which is just to say they will work, but probably better to take a closer look if you're planning to put this into a product or service and deploy it. But with that being said, there is a number of implementations, which is great, and they're available mostly on GitHub. And for those of you that are interested, which I think is most of us, hopefully, about what is being put in there, then yeah, this is the quick list of topics that you might want to look at. So what is a zkStudy? What is the core part of that? Well, the zk part, of course, is zero knowledge, meaning that there are private inputs and they can be shielded. The other important part about a Stark is that they're scalable in the sense that you have a proof of computation that's lasting t cycles, so that's bounded. And you can generate it in roughly t cycles as well. So what that means is, as you're generating the proof, this isn't exponentially growing as you're doing the generation. The next very important part is that verification is exponentially faster than the t cycles. So roughly it's log t, and this is a great property to have. And the example that Eli gave, which I think is pretty nice, is that if you had 1 million cycles, then the log t of that is 13. And if you go to 1 billion cycles, then the log of that is 20. So for those of you who've forgotten log maths, this is really great. Whenever you see that something is log t, yeah, it's going to scale quite nicely. The other important part of a Stark is the T, which is transparent. Like roughly what this means is that there's no trusted setup, and slightly more specifically, it means that verifier messages are using public random coins, which is being based on interactive Oracle proofs. The next part of the Stark name is that it's an argument of knowledge. So the proof is only generated by the party knowing the private input. So this is something important for the zero knowledge kind of family of algorithms, is that if you know a secret, constructing a proof does not reveal that secret. And of course the output is that there's a witness statement that can then be proven. And with all of this, you have formally an efficient procedure that the prover can make a statement, and then it can later be verified by anybody. And to then say, if you have a Stark, what is a snark? The only, roughly the only difference is that snark is simply a succinct, non-interactive argument of knowledge. Starks are also non-interactive. What this means is that the prover is able to do all the work up front and publish one statement, and then anybody could come and do the verification later. The first paper in 1985, I think, was largely driven by this. They were trying to look at interactive proofs and move it into a non-interactive setting. An interactive setting would be one where the prover is in a kind of live communication with a verifier, and the verifier is choosing questions to pose to the prover. And so a non-interactive setup is nicer in the fact that you don't need to have both the prover and the verifier online at the same time. The verifier could be anybody in the world at any time in the future. So this is really nice that you as an individual don't have to trust, but can verify yourself. And you don't need the prover to be online and ready to answer your questions if you wanted to verify. So moving into kind of the three main algorithms that are out there in the world and deployed. As it was said in the talk, there's many others, and definitely more are coming in the future. But these are the three that are deployed and are in use right now. So the comparing and contrasting, having a Stark prover, it's somehow quasi-linear to the naive computation. Naive being that there's no zero knowledge aspects at all. Snarks are very similar. The main difference is that you have this setup, and specifically that the setup is scaling linear to the computation and the prover time. There were some really nice graphs that were in the presentation. So for those of you that want a bit more of a visual of this, maybe later I update these notes and I'll drop a timestamp in there. But really what this means is that as the circuit is getting bigger, the snark setup is also getting bigger. And this has some concerns because already the setup is quite a special ceremony. And as you need to do more work during that setup phase, then you're going to, it's going to take longer, or you might want to increase the number of participants if you're doing some distributed computation. And the reason that the setup is not so nice is that if you're doing a snark, that means you're trusting the setup and that entire ceremony. And yes, the keys are getting larger as the computation becomes larger. Something kind of new that's being done with this CODA project is recursive snarks. So by using this idea of epochs, you're not growing the setup because the computation is being bounded by epoch. So in the case of CODA, they're saying that every block would be a new epoch. So if you have a known size of block, then this would be how much or how large the key would need to be. Oh, I see that the formatting is interesting. That's supposed to be nested, but yeah. So you're breaking the computation down into a sequence of epochs. Something that was a bit of a jab, and I hadn't really thought about, was that even if you're delaying by one block, this might not even be enough time to generate the recursive snark. So block time is important, and still to say that with this recursive snark, there is still a trusted setup going on because it is a snark after all, and the proving time will be larger. So bullet proofs have a great proof link. That's a really nice property of using this setup. The verification time is super linear along computation and proving time. And what this means is that verifying isn't fast like it is in Starks and Snarks. So when you're doing a large computation for proving, everybody who's verifying is also going to need to do a large amount of computation for verifying. So I think one of the main things that Eli has in mind is scalability. He mentioned this very often in his talk, and bulletproof is kind of out of the race then, because if the verification time is scaling along with the prover, then you're not really the network is not really reaping the benefits of this, and bulletproofs would, I think, be the wrong approach there. So something to say about all of them is that they're all using Peterson hashes, and so these are being deployed right now. Like Starks are very much being researched and released in a way by Starkware. Snarks are being used by Zcash, and bulletproofs are being used in Monero. So why do we want to do all of this? In the sense of Starks, why, if we have bulletproofs and they're good at some things, and we have Snarks and they're good at other things, and they're existing, why do we want a Stark? And it is really about the T in the name, which is transparency. So removing the trusted setup is pretty important. Even if you're doing this distributed computation, there's still the single point of failure in the sense that you had this setup phase at all, and it adds overhead to being able to use this cryptography. So it would be nice to have a Stark because anybody can do it at any point in time. Somebody who wants to prove a statement can simply do the computation, publish the witness and the verifier key, and then they're done. They could disappear from the internet forever, but anybody would be able to come and verify that into the future and not need to worry about who or what mysterious group of people did a setup. so there is something to be said about. I don't fully understand what he meant by this, but there is something to be said about relying on symmetric cryptography. I guess until now, it's been stated that it's post quantum secure. So it's not something I'm very knowledgeable about, but I have heard that using symmetric cryptography specifically, there is not a big advantage if and when we move into quantum computation, which is quite nice. And so future proofing is a good thing to have. I don't know if Stark. The reason I don't know is I don't know if Starks are the only ones that have this, but um, yeah. Um, so additionally, there's simpler constructions, and you're building on years of implementations. So using CRH and Fiat Shamir, these are things that have been existing in the world for a while, and so the mathematics I think is a little bit more known, and we're moving away from this so-called spooky moon math if we're using mathematics that have been around and understood for a while. So for Stark scalability, this was where this was one of the things I think that Eli was driving. It seems I think he's doing it because they're on commission with the Ethereum Foundation, and so this is why scalability is something that they're very interested in, to be able to deploy it into the world in Ethereum blockchain. So he had an update where in 2017 at the Consensus conference, they had one transaction, and the size of this proof was 500 kilobytes. And then in this year, they were able to show 500 to 80 improvement kilobyte size, and now they were able to reduce that further to 45. He was very optimistic about saying that they didn't yet identify a lower bound, so they're going to keep looking for improving that number. And already that's pretty fantastic, I think, to take it from 500 kilobytes to 45. It's still quite large compared to Snark and Bulletproof, but that's good to know that they're saying they're going to keep driving that number down. A really nice number, and something that I had not been aware of, is that if you're batching, so if you were to put 10,000 transactions and make a proof out of this, they were able to change, they were able to improve that number from 190 to 135. And so this was something I hadn't thought about, that if it's 45, kilobit for one transaction proof, to put 10,000 more is only moving the number up by a factor of 3, and that's pretty that's pretty impressive, and likely is. I think that this is where we're going to see. So this is my bias as an engineer. Likely, this is where I see that there's going to be actual implementations and use cases of this. I don't think that there's going to be a lot of cases where one transaction is having a proof made on it, but instead large batches. And so that's good to know that the size of the proof isn't ballooning when you're doing these batches. In fact, it's pretty great. And so to compare and contrast, then, when you take a look at what a snark is, when you have one transaction, you're getting 200 byte. If you're putting 10,000 transactions in, you're getting 200 byte. This is one of the nice properties of a snark, is that you have a constant size of a proof. However, if you're doing a snark, then you have a setup, and the key size is going to grow with the size of computation. So for one transaction, you're at 500 megabyte, and if you're at 10,000 transactions, you're at 500 gigabyte. So this is a problem, and that's simply part of the construct of snark. For bulletproof, to compare and contrast, one transaction is 1.5 kilobyte, and 10,000 is 2.5. Yeah, great proof length, nothing more to say there. The trade-off is that verification time is scaling linear with the proving time. So you don't get this this nice fact that the verifiers are going to be able to keep up with a prover. If so if you're using this. If you're using this in a blockchain, so if you're wanting to verify everything and you're looking at Monero, then yeah, all the verifiers are also doing quite a lot of work to do verifications. So then moving in more to Starks then. That first part of the talk was comparing and contrasting, kind of showing the current state of all these techniques, and especially of the improvements they made with Stark. So how to build an efficient Stark. Again, the high level or the gist of it is that you're going to take some computation and you're going to put it into this thing called AIR, which is Algebraic Intermediate Representation. He made the special note that this rank 1 CS, which is used in Starks, is technically a special case of an AIR. I don't know enough to kind of unpack what he said there, but good to know that kind of AIR in a way is like a superset of what was being done in Snark. So I don't think that all of that work is being thrown out as they're moving into Starks and taking a look at constructing circuits in this way. So when you're going to build one of these, you're taking the state of computation and you're making a sequence of field elements. And in the computer, you're just going to capture these in some register, which means it's deterministic, and you're going to just bind some variables to some values as you're moving over a sequence. And the overall program then is going to be represented as sets of constraints as you move from state to state. And these constraints are low-degree polynomials. Longer term, there should be some tooling that's going to convert programs directly into this AIR. And medium term, and I think already we see this, there are some DSLs, domain-specific languages, that are good for doing certain types of computations. He then moved into two examples. The first one being a Fibonacci sequence. So with Fibonacci, you always give it two numbers, and then it's giving you a result. So for Fibonacci, you can start with 0 and 1 or 0 and 1. You people know who you are, but yeah, you can start with a given state, and the spec is you have two field elements, which are the latest two, and then you're going to repeat this state n number of times to get the final Fibonacci number that you wanted. So the constraints for this is that you're going to make sure that one registered has been copied into the next one, and that you have an addition of the previous two. This is the high-level spec of Fibonacci. And the constraints you're going to have are for equality and addition, which is the AIR. And then jokingly, it was simply stated, and then you're just going to apply more crypto and algebra. Of course, it's just that easy to sprinkle some of that on top. He has posted some talks that he did at Technion on YouTube. I'd very much like to watch those. I haven't yet. And additionally, there was a 3-part blog post from Vitalik, and I linked to it here. So the Stark series from Vitalik, especially here, I think this is where he was talking about VDF, which is an important part of this. And so for those of you interested, or for a future talk that we have, it would be good to kind of unpack that and get into the maths there. Another example is a Peterson-Merkle path, which I think is pretty important. A lot of things end up being Peterson commitments in this world of zero knowledge. And so this example is you want to prove that you know a leaf in a Merkle tree of depth D when the Merkle root is R. So yeah, this is like if you only had a Merkle root, which is usually what is published, you don't necessarily need to know everything that's in the Merkle tree, but you definitely want to know that top node. What is the value there? And you're going to say, I know that this leaf is existing. And so yeah, the Merkle root is usually put into the public. And knowing that leaf then can be used in some interesting ways. In the zcash sapling circuit, it's used for shielded transactions. It's now using Peterson commitments. In previous versions of zcash, it was SHA-256. And if you're doing this VDF construction, which is verifiable delay functions, where, yeah, this is a way of trying to say, in the future, something will be, something will be revealed, and it's a verifiable delay in the sense that how long the delay is, whether that is, an epoch by timestamp or an epoch by number of computation cycles. You can make a proof out of that. And one way is to say, I'm going to hash this many times, some millions of times, and you won't know what the result is. So given an x and then hashing that some millions of times, the result is y. And you can make a proof out of this instead of also needing to do the computation of hashing x millions of times. So he gave some specific numbers that if you're going up to a 256 depth of the path length, then proving time is something like 7 seconds and verification time is something like 10 to 20 milliseconds. And yeah, most of the work I guess right now in Stark is verifying Merkle authentication paths. And yeah, what are some use cases of using a Merkle prover? So yeah, you can prove that you know a leaf, like in zcash. You can prove that account balances are being updated correctly. So when all of your accounts are being represented in a tree, if you're applying a transaction, you shouldn't be creating or destroying value. You should be moving it from one account to another, and you can do this. And yeah, similar for proving that trades are happening correctly. You shouldn't be creating or destroying value with any luck, and you can prove this. And all of these are reduced to the statement that you know a Merkle path to a leaf, and the Merkle root is a public value. So when we're doing all of this type of math, there is a degree of error that are in these systems. And this is where you're going to tweak the parameter for how much security. Specifically, he was talking about 80 to 128 bits of security. It's something I would like to understand better myself because these numbers seem low, and I'm not sure if that's a good instinct to have, but it was my kind of gut reaction at the time, and it still is. I think later in the demo, when he was running this Stark library on a phone, at first it was at 80 bits of security, and then he bumped it up to 128, and still on the phone the proving time was something like, the proving time was something like 16 seconds. So even at 128, it didn't seem like an outrageous number. So I'm wondering why that isn't higher. Maybe that's something about the way that they made the circuit or some other limitation that I'm just not aware of. Because yeah, the higher you move that security parameter, the complexity and the proof length are becoming larger or simply becoming more resource intensive for proving. Okay, yeah, and he did unpack it a little bit, saying, just jumping down, that at 128 bits, the verifier is asking 50% more queries than at 80 bits of security, and the proof length, of course, is larger. And yeah, that's something that we already talked about. Basically, this I would like to understand a bit more about tuning that security parameter. Possibly, I just need to do some benchmarking. But I would like to dig deeper into that in the future. So for all of these zero knowledge constructs, the math is being done over prime fields. And so with snarks and bullet proofs, I guess they're using some number theoretic assumptions, but starks are somehow generic enough that you're working over any algebraic domain, is the statement that Eli was making. And I guess this is important somehow, that you don't need to have a very specific pairing and a very specific elliptic curve. It's something that's very much out of my depth, but I know that when I don't know, the NIST or some other government agencies are making a statement about what primes to use, what elliptic curves to use, there's maybe maybe a bit of hesitation about wanting to trust that the government agency is giving fair pairings and that there's not some trick up their sleeve. So I think it's really nice that there are more people, more research groups in the world that are coming up with pairings and elliptic curves that are reasonably secure and are working for the type of constructs that they're wanting. And then it seems again with Starks that over any algebraic domain, it should be it should be possible. In theory, it's possible. I think that still in practice, there's going to be known pairings, known curves that will be used because optimizations, can be found there when those are pinned down, and then you build on top of that. Yeah. So the overall idea then. Okay. Yeah, I see that we're running a little late, or we're running exactly as we started. So goodbye to those of you who are headed out. So if we're doing, I think most of this we've kind of covered. That when we're doing larger proofs, you're going to ask simply more questions, but you can do splitting of the work over more rounds, and then. I think what's maybe more interesting, because interactive versus non-interactive is in a way assumed. I think what's, at least for me, what's more interesting was thinking about the potential uses, or maybe what the research is that he and his team are doing with the Ethereum Foundation, is being able to put Starks then into lower layers of the network to gain some aspects of scalability, possibly privacy in the application level. And one nice use case of all these zero knowledge proofs is that you could compress the amount of work needed to be done. And for those that are wanting to track state of a blockchain, light clients might not need to download the entire blockchain, because you're not trusting that some remote full node is giving you all the correct details, but instead you will have proofs that you could verify the state and still have a very small amount of data that you need to sync with the full node, because you would be able to have yeah, the proof coming in a reliable way, and then it's going to make bootstrapping and syncing much nicer for everybody. And so if you're scaling by putting some computation off chain, especially with Ethereum, there is there is a gas limit of something like 8 million right now on mainnet. I don't know if that's going to change much, because that will cause much larger block sizes. So if we want to do more computation, moving it off chain is quite nice then, both for computation and additionally for storage. So in the future, there could be something of computation nodes and storage nodes that are syncing or pinning their state on chain. And again, if you're verifying something like 10,000 transactions, you're only doing 3x, or you're only increasing the proof size the 3x of a single transaction. So there's something to be said there where these side chains could play an important part of scalability. Not everything needs to go on chain, and instead you're rooting trust on chain. And at least for me, that seems like a reasonable way forward. And so if you're scaling by batching, then when we have all of these tokens that are on chain, you could instead be signing transactions to a prover node on one of these side chains. You'll do the same signing as you do today, but the prover node is going to be able to batch together thousands of transactions and then making a single statement on chain. And then the state transition, balances of accounts can move. And again, if you're using and like a Merkle prover, then there's going to be a statement made that no tokens were created or destroyed. All the transactions were done correctly, and the final balances of all the accounts are what were expected. And then the verifier is going to be, committing state updates to storage instead of saying this account with this balance. And it's something very similar in a way with payment transactions. I think one thing interesting here was that there's a centralization trade-off, and he said unless it's done by the miners, it's something a little off topic, but yeah, I think centralization could be an issue here, or what these side chains look like could be an issue here.
Also, that idea of having just a verifier commit updates to storage. Sorry, I'm going to jump in a little bit.
Please. Yeah.
That's not just Starks. I mean, that's all like that's been proposed for all sorts of like other zero knowledge implementations. So it's interesting. I mean, it's an obvious use case, but I don't know if it's like better with Starks.
Yeah. Yeah, absolutely. And so that's kind of. I mean, we're kind of at the ending. I feel that I'm just reading the examples now, and additionally, Alex's notes had a really thorough walkthrough of what happened in the demo. I think it was down at the bottom. So for those of you interested, you could watch the talk or read Alex's notes. And yeah, so that's everything, I guess, in my notes. Sorry if that was more or less than what you wanted. We could have the meta talk later about how the talk was, but I don't know.
I thought that was great. It was super nice to have you go through these bullet points. And it's also really nice to see. I know the format's kind of interesting. We're so used to seeing presentations with like visuals, but like actually your bullet point notes and then explanations. Personally, I'm finding this really useful. So thank you for doing that. That's at least my take on it.
Nice.
I don't know if Alistair or Philip have anything they want to share. They're still there.
I'm still here. Yeah, no, that was good. Surely in the morning we'd have questions then.
Yeah, I don't know. So the purpose of this is that I wanted us to kick off. So if you have questions, I could maybe say yes, or maybe it's the questions turn into future topics, and maybe that's where we're at. Like what other things would we like to do with this working group?
So I did have a few things that I marked down as like notes. So one was there's always talk about how Starks don't need a trusted setup, but I don't understand what they do instead exactly. Or I mean, maybe that's like I don't know how a Stark starts. If you understand.
Yeah.
What I mean, like I understand now how a snark starts.
Right. Right.
So that would be something that I'd like to explore a little bit further. That was one that I had a little note on. The other one was when they talked about recursive snarks. I wondered if I did.
I think we lost you there. Are you still talking, Anna? You look a little frozen. Is she frozen or am I frozen?
She's still frozen.
Okay.
I think we can still talk.
All right, I'll tell her in Telegram. All right, yeah. I guess what does everybody else think? Do you guys have notes? Because maybe we could sync all of that into Google Docs as open questions, or maybe you guys already had topics that you wanted to dig into.
Well, I know I want to understand how Starks work. Where we're at with scalability, where we're at with actually implementing this this thing, where Starkware are at. Whether these things, how feasible this is right now. What are the limitations? That's what I want to know.
Mm-hmm.
But to get there, you probably want to look into what the actual technology is, how it works.
Okay. Yeah. I liked Anna's question, to be honest. I don't really know how to build a Stark compared to a Snark, because a Snark, you're going to do the setup, and then the desired outputs of that step are the verifier key and the prover key, and those both become public values. But I don't know in a Stark, does that just simply mean that there is no prover key and it's simply done in process, let's say, and the result then is just the proof and a verifier key? I don't know if anybody on the call can answer that.
Are there keys? And so this doesn't use public key cryptography at all, right?
Okay, right. So like prover key, verifier key, as in it becomes input. It becomes input to a function, right?
So not yeah. This is not how Starks work.
Okay.
Right? We only have hashes.
Hashes all the way down.
That's like almost all the cryptography.
I like the sound of that. All right. Hey, Anna, you're back.
Almost. Probably not. Yeah, this is why I need to.
Can you hear me now? I could hear you from. I noticed when I froze, but then I could hear you for a while. So
okay.
I followed everything you said. So yeah, that question that I had originally of like how instead of a trusted setup, but Alistair, I guess it doesn't even factor in if it's just hashes.
I know. I think they're obviously they use it to curves or something. I tried to think. I don't know. This is why I want to know the technology. But it's not like that.
Okay. So do you want to put that? It would be great to add that somewhere as a question as well.
I'm taking some notes.
Start.
Yeah, I'm taking some notes right now.
Yeah, we can see your screen. So
great.
And then yeah, and the other question that I had said, I don't know if you guys heard me, but it was the recursive start question. The question is something like, is that a thing? I think.
Fair.
What else would we have? Let's see. I mean, there was a part where you started to go into sort of the transaction details and like why, like it's so much faster. I mean, I think I still have a question mark as to why, but it's cool to see that, like to just be like, okay, this is where it's at. This is how it scales so far. The fact that you can do like, if you do, many transactions, the amount of, I guess it was like the kilobyte size of the proof didn't increase that much. That's what I sort of understood it as.
Right.
Well, this is the great thing. Everything is scaled as logs.
Yeah, and that's why, I guess, right?
Yeah.
Okay.
And it's going to scale to way more than 10K and still be very small. And that's when, even though these things are big, they're still going to be useful.
That's my bias, but it sounds like it's other people's biases as well, is that it's not just the research and the mathematics behind it, but it's also how can we wield one of these Starks and apply it in the world. So I really think batching is kind of where this will get used the most. Moving computation off chain is kind of necessary, and so being able to kind of compress many transactions, many messages into one transaction that occurs on chain. I think that this is important and probably where we're going to see it used, at least in the beginning, because who knows what other applications we might have. But I think in the future, and again, it's also where this research is going when I understand what is the relationship between Starkware and the Ethereum Foundation. Um, so yeah, I'd also be curious to know what it is that Coda, like where Coda protocol is at, because yeah, Eli was it seemed like, very nicely, but it seemed like he was ribbing Coda protocol a little bit in the sense of, does this work in practice? If you have faster block times, are you going to be able to have this recursive snark keep up with the blockchain, or was it like, was it even meaningful to do this?
Well, I'm happy to say that I think I might have mentioned this in the last call, but we just did a recording with Coda, and it should come out in like 2 weeks. And I'm actually doing the edit right now. So definitely, like, if we want to do a session on them, we can use that as a primer, like just to hear, because I actually asked that question of like where they're at, and so they've released. They actually have open sourced their code this week, last week, and they are live. So you can look at what they've done so far.
Nice.
And I think that would be really neat. And I think actually the timing might be good because it's in 2 weeks that we'd release it, and I think people would need some time to look at what they've done, and also it would be good for us to hear like feedback on what they've just released as well, like from other people. So, yeah.
Nice.
But I think that could be a cool topic.
Yeah.
Sure.
I mean,
I'd like to sort of dive into how these things work before talking too much about all the exciting things other people have done they're doing, because otherwise.
How would you recommend doing that, Alistair? Like, what's your process for getting inside this stuff?
I don't know. So I sort of been reading papers and going backwards, trying to work out where all the this stuff comes from, so I can start understanding something like the start paper.
So would that be a good goal then, that we maybe figure out what are the building blocks so that we could get through the Stark paper, or do you want to start at the Stark paper and then figure out if we need to take a step back?
Well, that's the tricky part, isn't it? Where do we start?
if the paper oh, sorry, please.
I know, you go on.
So if the paper is the goal, we could try to do a read through of the paper, and then we might come up with a roadmap of, okay, these things are important, and we don't grok it yet, so we got to go learn that, and then that might also, I don't know, that might also be a nice sensation to read the paper and then come back, some weeks later and go, aha, and we might get more out of it. Or
sure, yeah. Some people suggested we start with a paper. Some people suggested we started with Vitalik's posts and starts.
Right.
Oh yeah.
Which are also nice, but also get very involved quickly.
Yeah.
Oh.
Yeah. Has anybody else tried to read them? Because I made it through the first one, and it was a lot. I had made it through the Snark ones, I guess, the previous afternoon, so I was trying to power through, but I realized I was out in the ocean swimming for sure.
The first one's very high level, but by the third one is full of Python snippets and examples and maths. So it's interesting. It's actually very hands-on. So I'm sure the developers of this might appreciate that.
Okay.
At it right now. I think the idea of this was to do the high-level session, which I think you've done really nicely, because I think it was quite straightforward to follow most of what you did. There were parts where you even got like a little deep for my knowledge, but maybe it is like, I know that was the original idea a little bit, was why don't we do this high-level intro so we understand what we're dealing with, and then possibly go through the paper. But I wonder, like, paper versus Vitalik's post, which is better? The posts. Which do you think would be better for this format? Because maybe the paper is just something you read on your own, highlight what you don't know, whereas the blog post could be something we could actually, like, dig into. I don't know. I haven't even looked at the paper, so I really can't say. Blog post looks like it could be a little bit more manageable in a session. We can also leave this as we can put this question to the group as well, and just like see what people want. But I think that could be the next follow-up, is to start going into this one way or another, either through his posts or through the actual paper.
Yeah. Yeah, if nobody on the call wants to raise their hand to pick the next topic, then let's pose it to the Telegram group.
Yeah, I think that's good. And I think another thing is, like, Matthew, I thought you were great presenting. So if you want to do any other presentations like this, I really, at least personally, I followed you really, really nicely. So yeah, if you're like, I hope you're walking away from this being like, yay, because it would be great for you to do it again on something.
Yeah, thanks. Yeah, I would be down for that. I think I'd like to prepare a little more, going from a Monday a Monday evening saying yes to presenting Thursday morning. I didn't really prepare anything other than reread my notes. But yeah, I would also I think I would like to figure out the format, because I'm agreeing with Alistair. I like doing this high level overview, but that was more me sharing. I'd also like to be a little greedy and have someone present something I don't fully grok yet, or figure out how to do an interactive session where, as I've never done this before except for in university time. And in university time, it was maybe preparing for a midterm or a final, and as a group, one person would answer a question, but we don't really have a textbook full of questions we're trying to answer. So so this is where
I don't think we're going to have a shortage of questions.
Yeah, and maybe and maybe a short, like, we don't have a teacher, so I'm just going to throw it out there. There are there are talks from Eli at Technion where apparently he's supposed to be unpacking Starks as well. I think that there was 2 that are supposed to be very technical. I wonder if that is going to be a better place to start than reading the paper. At least for me, when I don't fully understand the math, I do like having a little bit of a human touch as opposed to just words on the page.
Sure, yes. No, the talks would be good. I mean, so what we kind of need to do is somewhere to have a high-level overview of what the tools are that go into a Stark. Someone must have a picture somewhere.
Right. I guess, do we want to start with pen and paper, right? As opposed to trying to build a circuit would be way too much right now, at least for me. But is that the next step, that we want to do the pen paper mathematics and understand this a bit?
Well, understanding the mathematics, that's hard. Right, these things. I don't think
how
going to be simple.
How deep do you want to go? Like, how do you want to understand the math, Alistair? That's your goal.
I do, yes.
Yeah.
I don't know if I want to understand the maths and then explain it to everyone here.
You don't want to do that? Or you do want to do that?
I'm not sure I want to do that now.
I see.
That's going to be tricky. It's always... no, I could, maybe.
Right.
Some of it.
Is this a monad? Is this a monad scenario? You're gonna open that door, step into the next room, and then suddenly, zero knowledge proofs. They're burritos.
I don't know this reference. But good.
It's very...
All right. Well, listen. I think what we should do. I think given that we are having very much a meta conversation, I think it would be great to include the rest of the group in that.
Okay.
So I think if it's okay for you, I'd like to wrap the session and say thanks again for doing this. I feel like people are going to enjoy this video. I think your voice is going to be very clear, so that's good. I don't know how these questions are going to come through. We'll share this video, we'll share it with the group, and then all the questions we just raised about like what to do next, how to do it next, I think this is still something we need to figure out. And yeah, I'm really looking forward to seeing what we do next.
Yeah, great.
Cool.
Thanks for...
I want to clap, but I think it makes no sense on you, so I'll just... Yay!
Yeah. Casual presentation over formal. Really glad that we kicked it off, guys. Thanks for joining, and looking forward to the next one.
Cool. So I guess you can shut it down. And if you want to send it to me, I will I'll put those